Just a quick introduction. It's a great pleasure to have you, Georgia. Gkioxari, I don't know exactly how to pronounce the last name.
That was very good, very good.
Georgia is an incoming faculty at Caltech. She received a PhD at UC Berkeley under the supervision of Jitendra Malik in 2016. And since then, she's been working as a research scientist at Facebook or Meta AI for a few years, 6 years. She's done very cool work in object and action recognition, focusing more recently on 3D vision understanding. And this includes the development of the PyTorch 3D library that some of us have used. And she has received multiple awards, including the PAMI Young Researcher Award and the ICCV Best Paper Award and others. So Georgia, thank you for being here today and really appreciate it.
No, thank you. Thank you for the intro. And since, you know, we are a small group, feel free to interrupt me, like ask any questions as we go on.
Yeah.
Great. So yeah, so I've been working on recognition a lot. This is what I've been doing since the first day I started working on computer vision. This is what I do today. I want to keep doing. But as with everything in recognition and computer vision, we always have to be aware of where we are as a community and what are the next challenges. So this is a little bit what I want to talk about today. And I'm going to start with the very important question of what is visual recognition. And maybe a lot of you know, but you know, it's good to cover the basics always so that we are on the same page. So visual recognition is the problem of taking an image, any image, and understanding everything about it. For example, there's this image right here. You have never seen this image before. You don't know, you've never been in this scene, you're neither of these people, but you can instantly know what's going on. You know that it's a street scene. You can understand that there's people, 3 people actually in the scene. You can also understand their poses. For example, one is like facing out, like walking away from us. The other one is staring at us and so on. You can also understand the objects and also how the people interact with the objects and even the 3D nature of a lot of these objects. So this is what we would like for machines to do as well. Take any image that is new, we've never seen before, and be able to analyze it and understand all these semantic concepts about it. And recognition is the reason why I am so infatuated with it is because not only is it a very difficult problem, the baseline is human vision and how easy it is for us to solve this task, but it has really important impact on a variety of things outside of the computer vision community. And in particular, the 2010s were a fantastic time for recognition. And the reason was that all of a sudden we had thousands, millions or billions of images coming in, being uploaded by user at a variety of platforms, YouTube, Facebook, name your Google, name the platform. We're talking about a huge amount. And of course, the next question after having all this data is, you know, trying to understand it. What do those images contain? Is any of this content harmful? How can I understand what is in the image so that I know what I should show you as a user when you want to select something or something that we know that you're most likely to engage with. So these are all the questions that we had to address, both in academia, but also in industry. And this is why this field actually started flourishing and booming in the past decade with tasks such as image and video classification, and even more fine degree localization, detection, segmentation pose. These are some of the problems that I've been working on in these years. And it has been great to see a lot of these things actually not just publishing papers and developing models that do something with them, but actually see them being used in production and finding their way in a variety of applications. But this was a decade before, and we're entering sort of a new era right now. The reason is that some of these problems are already solved. Okay, that's a controversial statement. They're not solved to point where they're done, but they have found their way inside use cases. And on the heels of that success and the fact that we were able to make such great progress, we're now thinking about more important problems. One is trying to build another universe where humans are able to interact with it a lot more than just passively consuming content. Others want to build, intelligent systems that are able to perceive and then also do things. AGI, I don't know what you want to call it, robotics. These are now much more complicated systems, but they all are based on the ability to be able to recognize from visual data. And of course, at the center of this is 3D recognition or 3D perception. And this is the area that we are talking about now, and that will enable all of these fascinating new directions, not just in the space of autonomous driving, where of course 3D recognition is very critical, but it also enables all other cool things like real life 3D imagery to revolutionize the way that we communicate or interact with visual content. But more importantly, it's about building systems that understand and comprehend a lot better and a lot more robustly. And that is important if you want to build applications that are actually important, for example, in the environment and applications like in conservation. And the direction that I am most excited about, which is building assistive technology that can complement the human visual system and actually do tasks so that humans can do tasks a lot easier and more effective. So for that to happen, 2D recognition needs to graduate to 3D recognition. And this is kind of what I want to talk about today, how to think about this transforming 2D and all the things that we know about 2D recognition into 3D, and how to make this a concrete and scientific path towards understanding the problems and finding solutions. So I want to talk about tasks, benchmarks, models, and then potentially different solution in the space of self and semi-supervised learning. Okay, so I'm going to start off with sort of introducing the problem of 3D recognition, and some of you might be familiar with it. I just want to set the ground for the problem specification. So here, the problem is we want to take an image, again, any image in the wild without having any control of what it shows. And we want to be able to understand all the objects that are in the image. But we want to be able to do this by predicting their 3D properties, a 3D location. And this, of course, really nicely relates to 2D object detection, which is a problem I'm sure a lot of you have seen and maybe have worked on, in which an input image is being fed into a model. And we're asking for the model to be able to recognize its category, but also localize the object with a box. And this box is defined by its 2D center, XY, its 2D dimensions, width and height, and all that in pixel space. Now, 3D detection is actually similar, but also kind of not. Again, we want to be able to recognize all the object types, all the categories that we see in the image, but we want to be able to localize these objects in 3D space now. So the center is parameterized with XYZ, it's 3D center. The dimensions are now 3-dimensional, width, height, and length. And we also have a rotation R because we want the box to tightly fit the object and not necessarily be axis aligned, which is a difference with 3D detection. And all this now no longer happens in pixel space, but now happens in metric space. And this is exactly why the problem is hard. And this also makes the output live in the 3D space. For example, I'm showing you here where you see some results of the model I'm going to present in a few slides, where the input image is on the left. In the middle, you can see the 3D detections superimposed in the image. And then a top view that shows you actually the 3D layout, how these objects are positioned in 3D space. And of course, to do that, we need a data set. Data sets are important. I'm sure you know, and large diverse data sets are important. This way has made some of the most successful use cases in computer vision have been driven by the presence of large data sets. And for 3D recognition, unfortunately, there wasn't one. And so we had to come up with something with a data set that would be really good for this problem. And my authors and I, and this is work done by my postdoc at Meta, Garrick, we had this idea of bringing together all the existing 3D data sets. So in the past 2 years, there have been these incredible data sets that have come out in 3D space. They were not necessarily designed for 3D object detection. Some of them were designed for inverse rendering. Some of them were designed for point cloud understanding and reconstruction. But what we did is that we took them and we very sort of repurposed them for the task of 3D object detection. And that might not seem, I'm just saying this in one sentence, well, that was actually a lot of work bringing all these data sets together, unifying their semantic categories, and even unifying their annotations and cleaning up their annotations so that it's a good comprehensive data set for the task. And that has created the Omni3D dataset, which has diversity of domains and objects. Actually, it's over 234 images, 34,000 images, over 3 million instances, and 97 object categories. So it is 20 times larger than any existing 3D object dataset out there, and actually very comparable to 2D datasets like COCO and ELVIS, which have been predominantly used for 2D detection. And of course, to convince you or to perhaps, make you understand more some of these properties of the data sets, of the Omni3D data sets, I want to present a brief analysis of it. And of course, in comparison to the existing data sets. So first, I want to show you the distribution of the object centers on the image plane, just to make sure that, to see whether data sets are, what the bias in the data sets are. So if we analyze the distribution of object center in COCO and ELVIS, you get a distribution like the one that you see in the image. And so as you can see, there is a very heavy center bias here. Does anybody want to venture why that is? Why does COCO and ELVIS, these 2D data sets, tend to have objects in the center of the image?
People taking the picture. Oh, people taking
exactly.
Yeah.
So it's the photographer bias, right? Every time you take a picture, phone or your camera, you want to tend for the objects to always be in the center. This is not necessarily a bad or a good thing. I mean, if this is the distribution of images we want to understand, so be it, but it's good to be aware of this bias. Now, if you look at the 3D detection data sets like Kitty is a detection data set in the urban domain, you see a very different distribution. And this distribution actually matches the urban scene, where objects are either laid on the horizon or near street lanes. Then there is SynRGBD, which is another data set for 3D object detection, which is meant for indoor domains, usually student apartments and offices, where you see that the distribution of objects is actually a lot more spread out. And Omni3D is actually somewhere, I would say, in the middle of that. So you do have a center bias, but you also have it's a little bit more spread out in both X and Y. And in the case of the 3D data sets, we can actually do the same, but now plot the distribution of the objects as if we're looking at it from the top. So how are objects distributed in distance from the camera? And if you look at Kitty, the urban data sets, you once again see this very heavy distribution, which is specific to the urban domains, and cars kind of driving parallel to you, which is expected. SynRGBD has, unfortunately, a bias towards really near objects. Actually, the largest distance of an object from the camera is 5 meters. I'm sorry about using that metric system. But 5 meters is actually really close. It's like, it's something that would not be very fit to generalize to wider, the more diverse scene, where you can have objects way further away than that. But then luckily Omni3D has a much better depth distribution of the objects. And actually the furthest object that we get, like the maximum value of depth that we observe, is up to 200 meters, which is great. It makes, of course, the problem harder, but it makes it also more general. So this is the analysis of the data set, just to convey a little bit about, also what to be aware of when you guys are working with data sets. Okay, so, but this sort of made us believe that, things are looking good, that we don't have really anything to worry about when it comes to the data sets and the bias that it carries, or much more so than existing data sets. And having this data set, now we're kind of ready to see, okay, can we train a model or can we build a model to perform 3D object detection? And when we look at prior work, there is a lot of it, but because the domain and the subfield of 3D object detection computer vision has been really much separated into urban and indoor, a lot of these methods were designed specifically for these domains. So there's a lot of work on urban domains, a lot of work on these indoor Thunder GBD data set of close near objects, but there isn't really a general purpose model that tackles 3D detection on a diversity of domains. And this, I don't want to get into the detail of it, but you know, when you tend to work in a specific domain, you also tend to make your model very specific to the requirements and the statistics of these domains, which is something that hindered applying all of these methods to be general purpose. And so, yeah.
I was just wondering how, like this task itself, how underspecified is it, or like how solvable is it to begin with? Other than like, I guess if you're in a very specific domain, you can get very strong priors to do something.
Correct. Exactly. You can get very strong priors to do something because you can either by hand designing these or capturing them from the model. So how underspecified or how easy it is, let's maybe discuss this after I show you this analysis and then results. Okay, but I agree, this is a question we need to revisit. Okay. Okay, so then in the absence of having a general purpose model to even consider as a baseline for this data set, we had to design one. And I am a fan of dirt simple, effective models. I don't like complicated stuff. So that's the direction that we went to. And we call this model CubeRCNN. And you're probably all sick of all the RCNN variants. I don't blame you. So just a brief description of what it does. And I hope some of you are familiar with these concepts, but it's basically, it follows the mask RCNN meta architecture of faster RCNN, where you would take an input image and we encode it with a backbone that is a neural network. It can be a CNN, it can be a VIT, it can be your favorite backbone, no matter what it is, which encodes this image into a feature map. Now, from this feature map, there is a little network that we call the region proposal network that predicts candidate objects in 2D space. And this is usually trained with an objectness loss, but in this case, we switch it up to make it a IUnus loss. So basically the RPN network predicts regions and tries to learn by predicting how much the IU of the predicted region is with the nearest ground truth. And this is a great loss, especially if your data sets are not exhaustively annotated, which is the case for Omni3D. And it's actually very effective. So I recommend that you use it if you're working with these models. And then the next, after we have our proposals, our candidates for the 2D objects, following faster RCNN and the 2D object detection literature, we train a model that predicts the object type and also refines the box. So this makes the detections for objects more confident and more accurate. And this gives us 2D detections. And of course, now we need to lift them to 3D. So a separate little network will predict the box parameters for the object, for the 3D objects. And these 3D objects are parameterized by the parameters that I'm showing you here, which capture the 3D center of the objects, the 3D dimension, the rotation, and then a confidence value. And the output is 3D object candidates, and we supervise the network with 3D ground truth and use a chamfer loss. This is a point cloud loss where we are treating the objects basically as the 3D objects as point clouds, where the points are the vertices of the 3D objects. And the result is being able to detect in 3D space.
Just a quick question.
Yeah.
So this head is like, you predict like a 3D box separately from the 2D box, and like they're two separate, so there's no like camera intrinsics or anything to relate the 2D box to the 3D box.
Oh, so yeah, what do you mean camera intrinsic?
Like,
so you mean
like there are some intrinsic relation between where the 2D box is and where you predict the 3D box, right? So you predict those two independently, or you try to enforce some sort of.
Yeah, I think that I'm going to answer that what, like actually right now, where I'm gonna sort of describe to you what these parameters do and how you associate them with the 2D and the 3D properties. So as I said, we have 13 box parameters for the parameterize the 3D object. The first one is the UV. The UV is the 3D center projected in the image plane. So it's actually a 2D location on the image with, and also which when predicting depth can be lifted to the 3D center. So UV and Z is the depth that we predict for the object center, are lifted to 3D with the use of the focal length, which we assume that we have for all the images in the data set. So knowing focal length is actually important. Not only is it just sort of metadata of images, but it allows us to actually determine the actual metric scale of the object. Without focal length, things would be actually kind of ambiguous. So these are the two sets of parameters that lead to the object 3D center. Then we have the width, height, and length of the object, again in the 3D box dimensions. And P, which parameterizes the rotation of the object. So these are the parameters that we predict. And of course, you know, if I were to ask you, okay, now let's set up a training objective for this network, something that we would do, and this is sort of following prior work and what is usually done in the field, is that we would associate losses to all of these sets of parameters and weigh them to get the final 3D loss. And this is where things actually kind of get ugly. So we have 4 sets of parameters. They're all very different with each other. So what is the right loss for each of these parameter sets? And then of course you have 4 different weights that you need to tune in order to find an optimal solution or the best type of way to weigh them for the final loss. And this is hideous and awful because first of all, it puts the pressure on us to figure out what is appropriate loss for all these parameters that are so different with each other. For example, what is the right loss to supervise rotation with? This is actually an open question in the field. Or what is the right way to supervise depth with? This is also very task specific. And it would lead to a huge space, a huge space for us to do grid search with a lot of compute, which is really not ethical, but also not very interesting from a scientific perspective. So we're not going to do that. And instead, what we're going to do is that we're actually going to follow a different approach. First, we're going to get rid of this grid space space that we will do grid search on, and instead define the loss by entanglement, by entangling all these parameters, and then also introduce per variable loss of disentanglement. What do I mean exactly? Okay, so all of these parameters that we're predicting, all of these 4 different sets, groups of parameters, can actually compose a 3D box. And the function for this is actually, there's a closed form function for this and how to take this and construct a 3D box out of it, which is also differentiable. So we can actually differentiate it with respect to all these parameters. So instead of working in the 4 sets of parameter space, we're actually going to be working in the 3D box space. So what we're going to do is that we're actually going to take the 3D box, which is produced by taking all of these parameters as input, and we're going to compare it to the ground truth box with a chamfer distance, which is a point cloud distance. So now this loss actually takes all of these parameters in as input and computes one loss that compares it to the ground truth. Does that make sense?
Yeah.
Yes.
Quick question. In terms of rotation of boxes, you only rotate through one axis, so it's not. Yeah, exactly.
No, we rotate.
So P is 1-dimensional, 3-dimensional.
P is a 3x3 rotation matrix.
Okay, cool, awesome.
But it's being parameterized. But we actually use the 6D way of encoding it, which is from Howley's group. Like basically, how do you encode a rotation matrix? You can do Euler angles. You can do various things. We use the 6D parameterization.
Okay, yeah, I just
From Holly's group.
seeing now that it's bolded. Yeah, I didn't see that.
Yeah, it's bolded. So yeah, exactly. So it's actually like a vector for each object. Yeah.
So just to recap, you're taking all of these parameters, making an actual point cloud for every box, and then comparing point cloud distances between boxes.
Exactly. So now all these parameters are actually fused into one output representation, a point cloud, that is then being used to compare instead of supervising each of these parameters independently.
And just another quick question.
Yeah.
Sorry. Yeah. And how do you actually sample the point cloud? Like, is there some like differential from the boxes?
Oh, so the point cloud is actually the 8 vertices of the box.
Okay, I see. And you
So the point cloud is a actually 8-point cloud.
Okay.
Yeah. So exactly. And so now we're going to have to deal with treating these variables differently and defining different losses. But there is one problem. I don't know if you could guess what that is. But for the sake of time, I'm going to tell you is that the curse of entangling all of these parameters that it makes the model is now ambiguous about when there is an erroneous prediction where the error actually is. Is it because there was a wrong in the depth, or is it because there was an error in the rotation? So while this entanglement is fantastic because we no longer have to look at it as predicting different parameter sets, it actually inserts some ambiguity. And so this is where we're going to disentangle the entangled loss. So the way that we're going to disentangle it is that we're going to actually take the same loss, but for each parameter set, we're going to substitute all the other parameters with the ground truth apart from that parameter set. For example, for the UV parameter set, we're going to use the predictions, but in the B3D function that constructs the 3D box point cloud, we're going to input all the other variables, all the other parameters with their ground truth values. So at the end, the 3D loss is a sum of all the disentangled losses for each parameter group plus the entangled loss. Does it make sense?
Oh, yeah, that's a question.
Hi.
Yeah.
It's going to be a very naive question, and I hesitated to ask because I feel like there's a silly answer to this. But wouldn't the gradient? Oh, hello. Hi.
Hi.
This is a silly naive question, but I don't want to be confused with the rest of the talk.
No, it's okay.
Wouldn't the gradient take care of that problem?
Of which problem?
So you're saying that basically when you take these, six, sorry, it's more than that. I don't remember exactly. Like you have a set of parameters, right? And instead of regressing directly on that, thank you. And so instead of regressing directly on, those values and supervising directly, you're going and you're creating this 8-point cloud route. And you're saying, well, the problem now is that if there's a problem with one of these parameters that created this 8D point cloud, we don't really know which one is at fault. But to create that 8D point cloud, I'm assuming it's a differentiable forward process. So if your loss normally with a gradient should be able to know which, well, of course, it's not as good as when you directly supervise on these values, but the gradient should be able to tell you, okay, which one is probably the culprit, if you want, Or
well, let's let's say that this is a function. So the issue is that you can actually get two different or the same output 3D object, the same point cloud, the same B3D, but the values of the parameters could be different. Right. So there is an ambiguity because of that.
Got it. So it's not like a one-to-one mapping, and so it basically in case of a one-to-one mapping, you want to do this disentanglement. That makes a lot of sense.
So
exactly. So
here you're assuming that, for example, if you just rotate, you would get the same box, right? So you're assuming in this entanglement loss that only one of the rotations is the correct one in order to train this?
Correct. So for example, in the disentangle loss, let's say that for the UV parameter, which is the 2D projected center, we will use all the other values, the depth, the width, height, length, and the rotation to be the ground truth. And we will only feed the predicted U and V to this B3D function that constructs a 3D point cloud and compare that again with the ground truth. And so then there, we're going to take the gradient only with the UV, and this is where the network will understand which parameter group actually causes what, and correct itself.
And why do you escape the hyperparameter problem here? Because now you're back to having 5 terms. So do we need to?
No, exactly. So you're back to having 5, but you're back to having more losses that you're adding up. But these are all the same losses, so they're not specific to a specific group of parameters like it was going to be before. And also the scaling has been solved for you because all these losses actually are in the same space.
Yeah, that makes sense. Cool.
So you have gotten rid of the awful problem of having to define the special losses for each parameter group and having to figure out how to weigh them.
Yeah, cool.
And so the way that I'm getting into this is not because if you want to work on 3D object detection, but if you ever have a problem in the whatever research topic that you're working on, where you're trying to predict a richer output, you should consider maybe this entanglement and disentanglement as a way to learn more optimal losses. So hopefully it's going to be useful. And then a final bit to make 3D object detection work is, so I've defined the 3D loss. We have the 2D losses and the RPN loss. This comes from faster RCNN to 2D detection. And so then the overall loss to train this whole model end-to-end that does 2D and 3D detection is to sum all these losses. And of course usually people weigh them, but it has already been studied how to combine the RPN loss with a 2D loss. But now we have a 3D loss that we're adding to, and now that also needs to be weighed. There is a weight that should be associated with the 3D loss in the overall objective. And this is where you need to think a little bit about the problem and how you want to do this. So you're asking a model to take an input image and confidently say something about the 2D object, but also the 3D object. But the nature of the problem is that while a model can be very confident that the object that it sees is perhaps, let's say, a chair, and that it extends this amount in this part of in the image space, in the pixel space, it might not be as confident about where this object is located in the 3D space. So you want to give the model the freedom to be confident about 2D, but not confident about 3D. And the way that we're going to build that in is that we're going to introduce a 3D confidence or 3D uncertainty, the opposite of confidence, to weigh the 3D loss. So this uncertainty is basically the signal that the model tells you about whether it's confident about the 3D prediction. And so the X of minus confidence, minus uncertainty, which is the confidence, weighs the 3D loss, and then that uncertainty is also added to the final loss. And so what this basically does is that if your mu, if this 3D uncertainty is large, then that means the model is uncertain about its 3D prediction, and it will weigh the 3D losses with a small weight, but it will additively contribute to the loss. And if this mu, this 3D uncertainty, is small, then that means that the model is actually very certain, and that increases the weight of the 3D loss on the prediction. And of course, mu, we don't have supervision here. So this is something that the model has to naturally try to learn. So you can see this as sort of being self-supervised. It's something that the model can decide to do. Of course, the model is not incentivized to say that it's uncertain about everything because of the additive term. But it has the choice to say that it's not certain for some objects. If it is truly, if it would contribute, if the L3D, the 3D loss would actually be high. So it has that ability to sort of reason, quote unquote, I don't like to use this word, about how to balance its 2D confidence, 3D confidence. And this 3D uncertainty or confidence that we are introducing here is also now used to score the 3D prediction. So the score of the prediction is now the geometric mean of the 2D confidence, which is what your 2D detection tells you, and its 3D confidence. Does that make sense?
Yeah.
Okay. So this sort of concludes the model and how to set up the training objective. And now you would say, okay, well, we're kind of ready to train, aren't we? We're not. And the reason is of a source of variation that is very specific to 3D object detection, and it's not there in 2D object detection. And this again comes with the fact that you need to understand sort of what exactly we're asking the model to do. So the source of their variation is the fact that the images in Omni 3D are actually captured by a variety of sensors. As I told you, we are combining data sets published by various groups that use a variety of sensors for different types of purposes. And some of these sensors could be, commercial cameras, or they could be Kinect, or they could be your iPhone. The sensors really vary. And that's a good thing, because we want data and models to generalize across sensors. We don't want to build a model that only works for a specific sensor. But with that also comes an ambiguity that is being that is not present because of this variety of sensors that we have. And I kind of want to try to explain why there is this ambiguity by showing you these two images. So here you see two images of a car. It's sort of a similar looking car. The pose of the car is the same. It actually takes the same area of in the image space. So the images kind of look similar, and an image model might actually also say that these images are actually similar. But the 3D scene that is the underlying 3D scene behind these images is completely different. So what we have is basically we have two similar looking images, but the 3D scene is completely different. And the reason is that these images were captured with different sensors. And that is why the images look the same. And of course, I am not the one that said it. Actually, Euclid said it, that one input image can actually be explained by an infinite combination of sensors and object depth. Does that make sense? Okay, and this actually kind of comes back to the question before about how ill-defined is this problem? How easy it is to make a prediction in 3D space when we only have images. And one of the ambiguity and the reason why things are kind of difficult is because of this uncertainty of how objects are positioned in 3D, and the images, and the fact that the signal doesn't necessarily constrain the output space. And since we want to be able to detect the depth of the objects, we need a way to overcome this ambiguity or minimize it at least. And the way we're going to do this is that we're not going to work in the raw camera space. So we're not going to try to predict the depth of the object in this ambiguous space, but instead we're going to actually introduce a virtual camera. So a virtual camera will transform all the images and the 3D objects in our data set such that the underlying the underlying sensor is actually the same across the same data set. So it will transform the 3D objects such that the image and the camera intrinsics for all the images in the data set are the same. And this means that you no longer have this ambiguity of object depth coming from the variety of sensors in the data set.
So then
this is always a tricky concept. So I kind of want to make sure that if there's any questions, I'm happy to address them.
So to get the real depth, you can just scale it back using the focal length of the particular.
Correct. So it's just a very simple linear transform. Again, very simple, but the only thing it does is that it now constrains the depth, the possible depth or explanations of depth for the object to no longer be in an ambiguous space, but constrain it in a smaller space. Does that make sense?
Yeah.
Okay.
I guess you always have the focal length information about
So you assume that you have the focal length information. The focal length is known. What is still ambiguous is how to condition your model on the focal length to predict the right depth. And especially you should, when you're asking a model to regress, regressing depth is actually, when the space is ambiguous, it makes regression behave very badly. And so you want neural networks to be able to leverage all the power neural networks have. You want to constrain the output space into something that is more unimodal rather than multimodal. Does that make sense?
Yeah.
Okay, so this is something that we found to be very important because it allows us to actually train models, 3D recognition models from diverse sensors. And you're going to ask, okay, but if this is such an important question or problem, why are we hearing about this for the first time, or why did you wasn't there anything related to that solves it? And here is where sort of the state of the field comes in, and it's because prior 3D methods that try to solve 3D object detection actually were working on single data sets. So data sets that were captured by only one sensor. And in that case, you no longer have the source of ambiguity coming in from having various sensors in your data set. When all your images are all captured by one sensor, the ambiguity that comes in from varying sensors is not there. So it's not a problem. So dealing with that with a virtual camera allowed us to train a 3D recognition model on the data set. But it was also important because it enabled data augmentations during training. So you have all trained recognition models or computer vision models, and you've all used data augmentations. You take your images, you scale them, you do various things to them to make training more robust. Now when you're trying to predict 3D object properties, image augmentations actually impact the 3D underlying scenes in the same way the varying sensors impact the 3D underlying scene. And so virtual camera allows us to deal with data augmentations and boost performance of models purely by using these data augmentations. So it was sort of this one feature that allowed us to deal with two of these issues at the same time. And again, 3D actual data augmentations are something that is not really often used in 3D detection and 3D recognition, especially for this reason. So virtual camera nicely addresses that. And just to show you performance-wise, quantitatively, how virtual cameras impact performance. I will show you this plot so we report average precision in 3D space of QBAR CNN that is trained fully on the 3D datasets with data augmentations and with virtual camera, and then two model variations that don't have this virtual camera feature, or train with augmentations but control without virtual cameras. And you see that in both cases where virtual camera is not being added, performance is actually significantly worse. And virtual cameras is not something that's very specific feature for QBAR CNN for our method. It can actually be applied to a bunch of methods, prior work on 3D object detection. These are models that take a completely different, different architecture and different model design, but you can still apply virtual camera to them. And you see that when you do that, actually performance increases universally for all of these models. And I only show two here, but we have a lot more in the paper. So it's sort of a general purpose feature, which makes it great.
A quick question. Does the benefit, I didn't see correctly the previous graph, does the benefit come mostly from the virtual camera itself or the augmentations?
Both. But so the question is, what happens if you do what happens if you don't have virtual camera and do data augmentations? What happens if you don't have virtual camera and don't do augmentations? And actually both of them are worse. So you want to do, so the lesson is that you want to have, if you're going to have augmentations, you definitely want to have virtual camera. But even if you don't have augmentations, you still want virtual camera.
Okay, thank you.
Yeah. Okay. Great. And okay, so I really have a lot more to say, but I will skip some of the quantitative analysis. We'll go to the results just to show you some of these outputs. So these are sort of images from the Omni3D data set, and input detections impose the image, and then a top view of the outputs. When you're working in 3D, it's always nice to have top views because it makes the output space less ambiguous, and it's important for readers to have that visualization. It's actually good scientific practice, and for a variety of scenes. But what is more important in my view is not, to see the performance of the test set. I want to see performance in the wild. I want to download any image that there is on the internet and apply this model, even for things that it hasn't seen before. And for the first time applying these models, you actually get something reasonable. Of course, there's still a lot of errors. One specific one is depth. Actually, depth is the biggest problem here. How to accurately predict the depth of the object in metric space is still one of the biggest error modes, and something that the model is very sensitive on. And single images are great, but we also, living in this space of headsets and all of these fantastic applications, we wanted to see what they do when they are applied to streams of data coming in from wearable devices. And here you see a video captured from Project Aria, which is a project Meta that builds this kind of nerdy looking, but kind of fascinating headset piece, which you can wear and record what you see as you're walking through scenes. And it has a lot of things on it. Actually, it has 2 cameras, 2 black and white and 1 RGB. It has microphones. It has IMU so that you can get the pose of trajectories as you're walking around. And this is sort of an exciting new visual modality that we'll be working with more and more in the future. And so we wanted to see, how does our model for 3D object detection do when applied to a stream like that, which is very different than static images that are being taken by people that have stopped to take a picture. And here you see some of the results. And of course, natively, we also do tracking in 3D space, since our output lives in 3D space and we have the pose from the IMU, so as the person is moving around, we can actually start tracking objects in 3D. Actually, tracking should happen in 3D, not in 2D. And this is what we do. Okay, and of course, you see, I'm not showing you this result to show you that this is solved. I'm showing you this result to show you how hard it is to do this, but how this could be a plausible direction to start working with 3D models. Okay, so I'm running low on time, and I kind of want to give more time for questions. So I had like a second part. I'll try to, brainstorm with you on how to get rid of the need for 3D supervision, which is so hard to get, and instead try to come up with unsupervised learning for 3D. But unfortunately, I don't really have a lot of time. So I think what I'm going to do is that I'm just going to sort of go, okay. I will maybe spend 5 more minutes just on this direction, and just in case anyone is interested to work on this. And of course, I'm happy to chat more after. But
Yeah, I think overall the lab is moving definitely more towards 3D than what it was a couple of years ago. So
okay, great. So let me just give you sort of the more big picture. I'm going into details, but about what is overall the right way to go about 3D. And if we were gonna judge from the past and how computer vision was made successful in the past, one big part of it was supervised learning. So I know that there is a lot of hype and a lot of really exciting results, especially in other fields about self-supervised learning or learning without the need of supervision. But in computer vision, we have seen some of the most successful results with annotations, with having supervision, training with supervision to learn our models. And of course, this is great, but in 3D, this is actually very challenging. And the problem is that it's not easy to get large-scale 3D annotations. 3D annotations are hard to get. They involve very specialized pipelines. People, workers, Amazon truckers are not mostly equipped to handle these tools and to annotate in 3D as fast as they are in 2D. So are we ever going to get a huge data set, like maybe ImageNet size data set for 3D? Very unlikely. So this is where self and semi-supervised learning become so critical. Right now in computer vision, self and semi-supervised learning have been used a lot in the hope to increase ImageNet performance by a couple of points. But for 3D, they're going to be vital. This is going to be the only direction to actually build good systems in 3D, finding ways to use supervision other than 3D supervision. And this is something that I've been thinking about a lot. And I had a paper in this last CVPR trying to do this. So I wanted to build a system that would take an input image. It would be able to detect all the objects in 2D and then also lift them in 3D. So be able to predict the shapes and also their layout, how they're positioned in the scene, similar to Cube or Scene in Omni 3D, but this time without using any 3D supervision. And so what I came up with, this is more of a proof of concept and like not like a finished, product that you can apply, but more like a line of thought. So what I thought is like, okay, I don't have 3D supervision, but I can have 2D supervision. I can use multiple images, frames from a video or a camera rig, and I can leverage 2D annotations, which I know how to get. I can either rely on annotators to annotate, or I can use those amazing off-the-shelf 2D object textures that are now working so well to get these 2D annotations. And so how can one combine these two sources of supervision that are not in 3D space to get something in 3D space? And so the idea is actually very simple. So I'm going to have a video. I'm going to take a video, walk through the scene, let's say. And this video consists of many frames. And I'm showing you here frame 1 and frame 2, view 1 and view 2. And the idea is that I'm going to use one view as input and the other one as target. So that means that my model will take the input image as like the first image as input, and we'll try to predict something in 3D space such that it's consistent with a target view. And very quickly, what the model looks like, you have your input image, you have the backbone feature map, again, that encodes the image with a backbone. And you have an RPM that I'm not showing you here that proposes or detects candidates objects in 2D. And so for every object detected in 2D, I will predict its refined 2D box and class, similar to 2D object detection. And also I'm going to lift it to 3D by predicting its depth, Z, and its depth extent, and also its shape by deforming a sphere mesh. And I'm going to do this for all of the objects that I detect. And the output is going to be my predicted 3D scene. So the objects predicted in 3D space to construct the 3D scene that I'm viewing in my input image. Now, if I had supervision, I would supervise this output directly, but I don't have supervision. So instead of what I'm going to do is that I'm going to render the scene from a novel view, from a different view than the input that I know of. And I'm going to compare the output of the rendering with a target image. So here, I'm only going to be comparing the output of the rendering, which is a 2D image, with a target RGB image. So all of this is in 2D space. And for me to train, the only thing I need is basically a way to extract objects from images. And as I said, you can do this by either using ground truth or an off-the-shelf detector. And of course, I'm also going to rely on differentiable rendering since I want to propagate back to the model. And I don't know how much you know of differentiable rendering. In this case, there are a lot of great libraries out there. PyTorch 3D is one that offers this and allows you to project 3D scenes to 2D images differentiably. I don't want to go into the detail. There is a few critical points on how to design this model, how to set up the objective, and how to change from 2D object detection and its modules that were designed for 2D object detection for 3D, because 3D is a different problem. So I will not present that, unfortunately. But instead, maybe I'll show you some sort of results on what we can do with such a model. And I like always showing scenes that are kind of complex and have objects that are kind of wild, like this church scene, very hard. And so you could, this is an output that you could get, which is output, this image is the first image that I'm showing you here is the input to the model, and the output is the 3D objects that are in 3D space, and no supervision was used. And of course, this is only sort of the first attempt in this. And there's so many limitations, which means so many opportunities for future work. One is to sort of find a better representation for 3D geometry. I used meshes because they're quick, they're fast, they're efficient. You could use implicit representations, which we know are better at capturing 3D geometry, but are more expensive. But so how to make them more efficient and use them in work like this is definitely a future direction. A lot of this work was assuming static scenes. So how can we extend it to scenes with dynamic objects, scenes that have moving objects, which also means now that we need to model motion as well. And of course, scaling. Scaling is powerful, and how can we scale to a lot more training data? And this is the direction that I'm mostly excited about, especially in the wake of spatial computing. So all my model need is walkthroughs, like it captures videos of people walking around, and the ability with camera poses, and the ability to extract 2D information. We have figured out how to extract 2D information. We have all of our nice 2D recognition models, but how can we get large amount of videos with camera poses of scenes in the wild? And this is where spatial computing comes in. The ability to actually walk around and capture such a diverse visual content wearing these devices is going to give us the next generation visual data that might enable us to learn better 3D models without relying on 3D supervision. And so this is why I think that, you know, the Zuckerberg and whoever else are excited about the business aspect of it, I am most excited about the new form of visual imagery that these headsets will give us that will completely change how we're thinking of recognition and perception and what we can solve with these new visual data sets that we're gonna have in the future. So this is sort of where the direction I'm excited to think about and pursue in the future. And so if any of these sort of directions click with you, please reach out, and I'm happy to chat more. And so, you know, just to summarize, there's a lot of great problems to solve in 3D. Most of them are unsolved and actually underexplored. Spatial computing is actually a great promise in this direction, and actually with tremendous prospect for impact in both industry, academia, science, everywhere. And you know, the advice that I give to myself, my students, and to you now is, you know, always build systems that work. It is really fascinating to see the work that we do actually being used by people outside of the community. So it's really, you're really fortunate to be working in a space that gives you that opportunity. So seize that, and I'm happy to take any questions now if there is any time left.
Samir?
Oh, hi. Thanks. So I had a quick question about the Omni data set that you were talking about.
Mhm.
So you said it was like around 200K
Yep.
images. And I'm just wondering, like, do you feel that given like the current modeling techniques that this data is sort of like saturated? Like, should we really be working on, like, is the bottleneck that we're not getting the most out of our data sets currently, or that our data sets are not big enough? And maybe the answer is
It's definitely not. Yeah, that's a fantastic question. So I don't know how you guys judge saturated. For me, saturated in my book means that a data set where performance is already kind of high, and the last bits of performance are like ImageNet is saturated. Let's just call it as is. Okay. The performance in Omni 3D is abysmally low. The AP something around 20%. This is like feels like working in recognition 15 years ago when we first started working with Coco, where performance was a 15. So there is so much more. So it's very far from being solved. Now, I think your question was, like, do you think it's going to be solved by purely working on the Omni 3D data set? No. I think that the way to solve this is not just by, it's actually by better model design and possibly by leveraging other modalities or other representations that will allow you to solve this problem. For example, detection is a bottleneck in Omni 3D. We can't detect all of these 2D objects. Like AP2D, 2D AP is not 100%. It's actually very far from it. So there needs to be innovation that still needs to happen in 2D detection to even solve for 3D. So this is not just a standalone problem to work on. It actually will require innovation in modeling and representation learning for a variety of visual tasks. But if you want to work on 3D object detection, I think that this is the data set to go for.
cool. Thank you.
More questions?
Yeah, save it for the one-on-ones.
Oh yeah, like people are saving for the one-on-ones. Okay.
Okay, sounds good.